Hello and welcome to the online physics classroom session. I am your online physics tutor bedprakash. So let's learn. Today in this fifth online physics classroom session on fluid mechanics, I am going to discuss with you Bernoulli's principle. This is presenting the shear relationship between kinetic energy, potential energy and the pressure energy on the liquid. The Bernoulli's principle is applied for critical computation related to the fluid dynamics. This Bernoulli's principle comes from the concept of continuity equation. The Bernoulli's theorem has allowed us to know about the relationship between these three energy principles on work and energy theorem. Now, to understand this Bernoulli's principle, we have to keep in mind certain conditions imposed on the liquid. This principle imposes on the liquid that horizontal flow of its nature. This is so because the fluid dynamics from the point of view of Bernoulli's principle has been calculated depending on the fluid velocity and density. So we have to keep in mind that drastic change in fluid velocity should be avoided. That is the only reason we are considering the horizontal flow of fluid. The drastic change of velocity of fluid occurs in vertical flow of fluid where sharp transition of fluid takes place. Besides this, the fluid should be incompressible in nature. Why is so? Because for compressible fluid, it has variable densities, or with the travel we have to take in consideration that with the condition of steady flow, so the fluid should be kept in constant density. That is the only reason we are considering the incompressible liquid. Why the Bernoulli's theorem is considering non-viscous liquid? Because from the definition of viscosity, it is quite clear to us that viscosity is the frictional force between the fluid surface and the inner wall of the flowing equipment through which the fluid is flowing. So we have to keep in mind that the frictional force acting on the surface of the fluid and the contact wall of the inner surface of the equipment through which the fluid is flowing should be minimum. By keeping in mind these three conditions, we have to understand the Bernoulli's principle in depth. For this purpose, we have to look into our board representation. So let's go to the board. So to understand Bernoulli's theorem, we shall consider irrotational steady flow of fluid which is incompressible and non-viscous in nature. Now to understand this, we have to consider a section of variable cross-sectional area based pipe through which a fluid is flowing. Let's see how it can be shown. Let's consider a variable cross-sectional based flowing pipe like this, and two distinct cross-sectional area, or say name as A and B. The cross-sectional area in this side A has A1 and in this side B has A2, and the pressure applied from this side is say P1 and pressure from right to left is say P2. The fluid from say A to A dash is traveling this amount of path with the time say delta t. It is also taking delta t amount of time to travel through this tapered part compared to this side, equal amount of time. Now with respect to a linear reference plane, the fluid is having different height as h1 and h2. We are considering this incompressible fluid is having the density of rho. For this particular side, since the fluid is flowing with a steady flow, we are considering that it has uniform velocity from this side as v1 and uniform velocity of this side as v2. For this particular distance of say a1, we can calculate it as v1 delta t, and for this particular distance of b dash as v2 delta t. To having an account of this particular portion, the volume of fluid it is keeping with as the volume of this amount of portion of the liquid A1 V1 delta T, and for this amount of portion will be A2 V2 delta T. The mass of fluid, that is the total mass of fluid, portion of total mass of fluid is over here, and the portion of total mass of fluid is over here. Both of the fluid is taking the same amount of time delta T to travel from this portion to the A dash, B to B dash. To calculate that particular amount of mass from the point of view of continuity equation, this both volume will be equal. That means A1 V1 delta T will be equal to A2 V2 delta T. Now if we are going to calculate that mass from the equation m equal to rho into V, that is the volume V, we can calculate that rho A1 V1 delta T equal to rho A2 V2 delta T. From here we can calculate the work done by this force. Now let calculate the work done by these two portions of the fluid. To calculate the work done, we have to first take into consider that number of force or the total force acting on this part of the fluid. The different types of force acting on this. First is the pressure force acting on this part of fluid from left to right is P1 A1. So the first force is P1 A1 from left to right. The second one is P2 A2, that is the pressure force from right to left. The third one is the weight of the liquid, that is delta M, the mass of the liquid, and the gravitational force acting on that particular liquid. Now the fourth one is the most important one, which we sometimes forget about, that is the contact force. That is the contact force, let name it as FC, contact force between the tube and the flowing liquid. So the contact force is acting on the tube actually. These four forces are actually acting on this particular system. From this point of view, we can calculate the work done by due to each of these force. For the first one, we have to take into consider that the fluid is taking delta T amount of time to travel through A to A dash. Now for this section, we are taking that from A to A dash, the fluid is taking delta T, hence it will be V1 delta T, the total path V1 delta T, and the work done by this force P1 A1 pressure force is basically P1 A1 into V1 delta T. From here we can write this as W1 equal to this. So this part, this is A1 V1 delta T, we can cumulatively write from this part as delta M by rho. We can write from here, right? So similarly for this part we can calculate the work as P2 into delta m by rho. Since the mass is same for this section and this section, and the rho throughout the system is constant, since we are taking the fluid as the incompressible one. What will be these two functional area we have to take into consider. Before going to the analysis due to the weight of the liquid and the contact force, we have to consider that this W1 and W2, that is the P1A1 and P2A2 force, is opposite to each other. So whenever we are considering the same signal, it will create a problem. So we are taking that as -1, since we are considering that the fluid is flowing from this direction to that direction. So we are taking the work done by this portion of liquid is negative to the work done from this portion. So we are taking a minus sign before this. Now going to the part of this section. So whenever we are taking into consideration of the weight of the liquid, then we have to consider that work done by the weight of the liquid is basically the change in potential energy due to gravitational force. To calculate the potential change in potential energy, we have to consider that potential energy at section A dash B B dash minus potential energy at section A dash B. That means potential energy acting on this section minus potential energy acting on this section. So basically from here we can calculate this amount of potential energy for this amount of liquid and potential energy for this amount of liquid. Now this can be simplified in the form as potential energy required for A dash B plus potential energy required for B B dash minus potential energy required for A dash minus potential energy required for A dash B. So from this both potential energy part of A dash B is getting cancelled out. So this is the remaining part, that is the effective potential energy will be potential energy required for B B dash part minus potential energy required for A dash part. Potential energy for this part is basically acting on this amount of height, and the potential energy for this part is basically acting on this amount of height. From the basic law of potential energy, mgh can be calculated from here, delta m g h2 minus delta m g h1. From here we can conclude that the potential energy is actually like this, but the actual gravitational potential energy change is basically the negative of the effective potential energy, because the work done by the weight is negative of the gravitational force acting on this. Hence we will take the negative of this, due to which it becomes delta m gh1 minus delta m gh2. That's basically the summarizing the scenario. So here I have deleted the velocity over here. From here we have done with this, this and this. Now we have to consider the contact force. The work done by the contact force acting over here. From the direction of this contact force, it is quite clear that it is exactly perpendicular to the direction of the flow of the liquid. Hence, since we calculate the work done by any force as its magnitude and its traversal distance with the cosine angle in between that, due to which we are taking as of that particular angle which is perpendicular over here, and the value for that cosine angle will be 0. So hence the work done by this contact force is actually 0. No work done by this contact force. So we are basically naming this part of kinetic energy gravitational potential energy force as W3. So the total work done can be termed as W as W1 plus W2 plus W3. So I am just deleting some of the portions so that I can write. So the W1 is P1 delta M by rho plus P2 delta M by rho plus W3 is delta M GH1 minus delta M GH2. So this is the total work done by this fluid in this system. We have just concluded the potential energy part of this particular liquid. Now we have to take into consideration the kinetic energy part of the particular fluid. To calculate the kinetic energy of this particular fluid, we have to consider the system of with velocity here v1 and v2 over here. As I have mentioned, kinetic energy of the fluid is like the potential energy. The kinetic energy in between this section minus this section will be a dash b b dash minus kinetic energy for a dash b. So from here, kinetic energy, this part can be divided into kinetic energy for a dash b plus kinetic energy for b b dash minus kinetic energy for a dash minus kinetic energy for a dash b. So this part is basically getting cancelled out with each other. This section is basically the actual kinetic energy acting on this particular system. So the kinetic energy for this part, that is over here, will be half delta m v2 square minus half delta m v1 square for this part. That's all about the kinetic energy. Here in this system, particularly the kinetic energy for this a dash b section, that means the dynamic part of this particular liquid, is opposite to each other, considering this section and this section. So it is getting cancelled out over here. Now from this particular section we can conclude over here work energy theorem, which is basically the work done by a force is equal to the kinetic energy of that particular system. How it can be done? So the total work done is this amount of total work done, and the kinetic energy acting on the system is this. So we are just equaling this. So we can write as P1 delta M by rho plus P2 delta M by rho plus delta M GH1 minus delta M GH2 is equal to the half delta M V1 square minus half delta M V2 square. From here, alternating the equation from either side, we can write as delta M, that is the mass of this and this amount of liquid common from this case. We can write P1 by rho plus GH1 plus half V1 square is equal to P2 by rho plus GH2 plus half V2 square. By multiplying rho throughout this equation, we will get P1 plus rho GH plus half rho V1 square equal to P2 plus rho GH plus half rho V2 square. This is actually depicting conservation of pressure energy, potential energy, gravitational potential energy, and the kinetic energy of the fluid is basically constant throughout the any portion of the liquid. So in other terms, we can actually write that the pressure energy, the potential gravitational energy plus the kinetic energy is constant throughout the total travel path of the liquid. This is the net derivation of the Bernoulli's principle. From here, we can apply this principle to different kind of applicational field to understand different complex problems, which I am going to discuss in my next session related to this application of Bernoulli's principle in my next online physics classroom session. That's all for today's session. Thank you for watching my channel and this session. Be with my channel, give a like for this and do subscribe the channel. Thank you.